Well, good morning, everybody. Can you hear me okay? Hopefully.
Yes.
Yep.
Awesome. All right. Well, welcome. Last two classes of the semester. You guys have made it so far. And today is going to be a more for fun kind of a class. It's going to be a little bit less structured. We won't have a formal agenda, but we're going to do the systems design workshop. And today we're going to kind of look at the the design of what we're going to put together. We're going to start it in KiCad, and we're going to kind of see this design through. And we'll go as far as we can today. I think this should get us to, hopefully we can get to flat cam today. And then on Tuesday, which is our last class, we're going to cover the actual CNC process, the manufacturing. I'll give you some tips. There's probably 4 or 5 lectures worth of content, but we're going to try to get through it. And we'll get as far as we can. If for some reason we can't see it through to completion, I can't get it on the CNC to cut, I'll try to post some video lectures so you can see it yourself. It's a really cool thing to do, and I hope you guys enjoy this. I've never done it before for a class. I prototype these boards somewhat regularly, but I've never done it as part of a workshop. So let me know what you think. I would say let me know what you think in the comments. But this is not YouTube, so just if you're missing something, if something is not quite working out the way you want it to, please post it in the text chat, and we'll go from there. All right. So I have been kind of deciding last minute what the hell we're going to build, and I have decided I would like to build a control pad for this automated gate control system that I have. So some of you actually may have seen this in 412. Let me see if I can if I can pull this up in a non-annoying way here. Let me just go to my channel here, and yeah, I think it's somewhere here. So I'm gonna go ahead and get the screen share started, and I'll just show you an example of what we're doing. Share screen 1. And we're gonna look at this, and I'm gonna turn off the sound because it's not needed. So my problem is I've got this robot mower, and I've also got kids, and we've got a fence with a gate. And this robot mower does not know how to get from one side of the fence to the other. Let's just boost that quality a little bit. This is looking a little bit annoying. Okay, come on. Oh, I wonder if it's not playing because of the screen share. Okay, so I've got these gates here. And I've made holes in them. I've got one on each side of the house, and I've from scratch 3D printed, designed circuit boards, cut everything out. The only thing I didn't make were, of course, the bolts and the gearbox and the motor and the wires. Everything else is custom designed. And the idea is we monitor this controller here with an whatchamacallit, what do we call it? A photodiode. And when this mowing light switches on, this little ESP32 based microcontroller or microcontroller board will send a signal over a long-range radio. It's called LoRa, and this is when it was still all prototyped. And then the gates will start opening. I don't know if it'll show it or not here. I think. Well, anyway, yeah, there it goes. That particular gate is an 80-to-1 gearbox ratio, and so you can see it opening that gate slowly. It'll go all the way up. This is before it was all finalized. Everything is final revision. This was still a breadboard in that box at the time, but now it's all custom PCB. It's been manufactured, and so anyway, gate opens up, mower goes underneath gate. It goes where it needs to on both sides of the house. Reason for this is I have kids, and my daughter escaped through this last year. And then my son actually escaped when the mower started going out just this week. So I've had to reprogram the mower to run at night when the kids are in bed. But anyway, this system works. And then when the mower goes back home, the gate closes. And so that kind of gives you an idea. But because this uses LoRa, the long-range radio, I want to add an extra control panel where I can nudge each gate open or closed. They're using stepper drivers and worm gear boxes in this container there, and it works really, really well. But sometimes if there's a power issue or whatever, maybe the gate gets stuck open. I have code in the microcontroller. I'm using EEPROM to figure out if the gate was previously open or closed during a power failure. But in any case, there may be some edge cases where the power fails during an operation. This is a fail-safe mechanism, so the controller, the device that is on the control pad that's registering, that's looking for the signal, it sends out a keep the gate open command, and if the gates don't hear the keep the gate open command, they shut automatically. I had once I used to have them both solar powered gates, but there are issues with the lead acid batteries and the charge controllers that I had, and the batteries would die over the winter. It wasn't too pretty, so now they're both running on AC power with a low voltage DC cable running to power it. The problem with that is if there's a power failure, which thankfully is extremely rare where I live, but it supposedly could happen, then you could have a gate that's stuck in an edge case. And even if the EEPROM thinks, oh, okay, the gate is open or the gate is closed, it's actually going to be in a halfway state and it's not going to know. Yes, I could add switches, I could add optical sensors and all that stuff, but those are things that go bad with the weather. The design that I have so far works extremely well in the weather. I'm kind of shocked. It's already a year old and it seems to be working perfectly. I've never had issues with the gearboxes, with the motor, with the controllers, with the steppers, none of that. So I like that. And the goal is to keep it that way. So I don't want to add any sensors that might be unreliable, that could get clogged, that could have grass growing on them. We're just going to go with the stepper itself. And then to do that, I need some sort of a control panel where I can send a little nudge command to each gate. And I have that right now, but it's breadboarded, or I just load up a custom firmware and have it send out a nudge command. That's just really annoying, and I don't like it so much. So we're going to build a custom version of this, which serves two functions. Number one, it's a repeater if I ever need it. I don't, because this long-range radio can go up to 4.5 kilometers in ideal settings. So for the backyard, it's perfectly fine. But it can serve as a repeater just in case. And the other thing it'll do is it will it'll have those buttons where I can nudge it open and closed. So I have my code base for these things. Let's see. No, that's not what I need. And I'll open up the screen share here in just a minute. So here is, I'm going to turn on the screen share again. Here's kind of the code base for these ESP32 boards. Just so you know, let's see if my screen shares. I'm using a device called a Heltec LoRa 32V2. These are cheaply available. You know, these are Chinese implementations of the ESP32. The chip is legit. But if you go to Amazon and look for SP32 LoRa V2, these units, you can get them in 2 packs for $50. Note, you'll want to get the 915 megahertz version. These are the ones that you can operate in the United States. They come with an OLED screen. They come with Wi-Fi. They come with Bluetooth. They come with the LoRa radio, which is the one that I'm using. And they're really cool devices, right? So again, 20, they're usually about $20 a pop. Sometimes they go up, sometimes they go down. And they can be interfaced in Arduino. If you're an Arduino, you have to go to you have to add the board in, and then you can go to the board's manager and pick the Wi-Fi LoRa 32V2, which is what this is. You can pick clock speeds. We're going to pick the frequency range, and I'm sorry you can't see that, but we're going to pick US 915. And then you can pick the speed. The default is 240 megahertz. But if you're trying to do power saving, that kind of stuff, you only need to clock this at about 80 megahertz, honestly, to do what this thing is doing. So I'm going to have a few pins that I'm going to use. And the ones that I'm going to be interested in are 32, 33, 13. These are bidirectional pins that I can use. And I believe there's one more. So I'm going to have 4 buttons that I'm going to input to this device. So in order to do that, we need to pull up the pinout. Yeah, there it is. And we're going to go to their docs. So sorry if we're kind of flying through this, but I'm trying to take you through the process from inception to product as fast as I can. So we're going to look at documentation, and we need the pinouts, and we're going to look at pins that we can actually use. Now, one of the things that I figured out on this board is there's a very limited number of pins that you can actually use for I/O. Many of these are purposed for the LoRa radio or are used in other aspects. I know for a fact I can use 32 and 33 here. I can use 13, which is on the other side, I believe. No, 13 is at the bottom. And maybe 12. So 12, 13, 32, 33. I believe these are the usable ones. Everything else seems to not work when I try to use it. I've tried 23. I've tried these ones up here. For whatever reason, they do not work. And more importantly, you also have to make sure that you're using pins that have interrupt capability. I believe all these are, but you don't want to override pins that you can't use. So for now, and I'm going to check this in between our class sessions, I believe we're going to use 32, 33, 12, and 13. So we need to route our signals from these. And the board we're going to build today is going to actually use this as a drop-in. Now, I could specify an ESP32, source to LoRa radio, all that kind of stuff. We don't have time for that, so we're just going to use this as a drop-in module. This has how many pins? A bunch, like 20-some pins on each side. So I'm going to show you the process that we're going to use to get that started. And the board we're going to make is a single-sided board, which is going to have some challenges in how we route things. We're going to use some push buttons, which I have through-hole push buttons because all I can make with this setup are through-hole. I can make SMD. I can make SMD for sure. There are some challenges with using SMD. I would show you how to use the reflow oven and how to do that. I've got a small one that we can modify and do that with, but I think we're going to focus on through-hole design because that's what you're probably most familiar with. If you want to find out more about using things like reflow ovens and SMD, we can certainly talk about that. But for now, we know that we have a system that uses pins 32, 33, 12, and 13. And these are how they were labeled in Arduino, but these actually map to different pin numbers. I'm going to leave this pinout up here because we're going to refer to this pretty often in the design process. Okay, so if you want to try this, I highly suggest these boards. They are really cool. Again, you can interface these directly in Arduino. There's a few things you have to do so you don't get into deadlock situations. I of course don't even have Bluetooth or Wi-Fi turned on here. I just use the LoRa system, and it works really well. And like I said, it's got a cool little OLED screen which lets you interface. All right, so I know I'm going to use pins 32, 33, 12, and 13, and we're going to refer in the actual diagram when we make it to this. Now, I'm going to pause here for a second and bring up a very important topic that we're not actually going to implement, but for those of you who are watching now and for those of you who are watching online, I want you to pay close attention to this, and this is a topic that a lot of people don't discuss. And that is using little filtering capacitors. And I cannot, for the life of me, think of what the actual term for these are called. And if someone knows what the term is, throw it out there. But we basically use them. It's got a term. There's 2 terms that get used, and I always forget the damn name. But they're little capacitors that we throw in between power and ground at any input, power input to a chip. And so those are important. We're not going to need these because this Heltec board has all of those built in right at the microcontroller level, but they are things that we may want to keep in mind.
Is it a decoupling capacitor?
Coupling, right, decoupling. Thank you. So I remember it like twice a day, and then every other time I never remember it. So here's a good example of a decoupling capacitor setup. So here we have an LM7805, which is a voltage regulator. It takes, up to 35 volts in and brings 5 volts out. And I'm not going to spend a lot of time on this because it's not an EE class, but what you want is some sort of decoupling capacitor between the power in and the ground, and you pick a capacitor, typically a few fractions of a microfarad in, because what that does is it reduces high frequency resonances and oscillations that are happening on the capacitor or on the power input, and then you'll have another one on the out. This is basically forming sorry, message I had to ignore. On the output side, again, these are basically RC circuits. We figure out the resonance that we're trying to get rid of, and you figure out based on the voltage and perhaps a switching frequency of these kind of guys, what kind of capacitor. But 0.1 microfarad is very common, and you want to put these as close to the input, the power input of the IC as you can. And what this does is it gets rid of noise, and you wouldn't believe what you can get when you don't have these. You'll have stepper drivers that are making noise. You'll have microcontrollers that aren't reading their inputs correctly. You'll have all sorts of stuff. So when you look at a PCB, a common PCB, you'll see tons of these tiny little decoupling capacitors all sprinkled all throughout the board on all the power inputs. These are important because they help get rid of those power fluctuations that can cause all sorts of instabilities, okay? So we're not going to use those today because all the inputs on this board are decoupled. But in any case, that is something to keep in mind when you're designing. If you're playing along at home and you're making a different design, you have power input, especially through regulators or especially across any kind of a distance. You'll want to add these decoupling capacitors. If you need to find out more, look it up, read about it, figure out how to specify the capacitor sizes. But again, for the board we're using, all the decoupling is already built in place, so we won't need to do anything about it, okay? But that is something that I did want to bring up. Now we're going to do a one-sided board because that's all I'm going to be able to CNC. I think we're going to go ahead and get started. So I'm going to go ahead and open up KiCad, and it is pronounced KiCad, not KiCad or anything like that. So I'm going to make a new project. Just put this in my temp folder. I'll just make a new folder, 525 project. Thanks Windows for, I guess, not updating that. Oh, there it is. Okay, 525 project, and we're going to call this, I'm going to end up moving this anyway, but we're going to call this Gatematic is the system is what I call it, Gatematic. Controller, let's see, controller is too generic. We're going to call this a, let me lift my microphone up here. We're going to call this, what am I going to, hand pad. So this will be my portable little controller. Okay, and I apologize, some of this stuff is going to be hard to read. I don't know how much I can change some of the fonts here. Some of these I just won't be able to, but I'll try to make them big enough so that we can at least make heads or tails of this. So we're going to start. I'm going to show you a couple things here. One of them is the footprint editor. So KiCad has EE Schema, which is a schematic editor. It has PCB New, which is the layout editor, and then it has the footprint editor. The footprint editor, and let me disable my virus scanner because this actually slows it down. Oh, it's already off. Okay. The footprint editor is a database. It's a library of tons and tons and tons of you know, pad layouts for parts, and whether you're putting an NFET transistor or a microcontroller or a resistor or what have you, there is probably a footprint for this. I'm not going to create the footprint for these boards because it's going to take us extra time, but I'm going to show you what these footprints look like. And what we're going to look at is, let's see, do I have the ESP? All right. I think I was using, all right. Actually, I think I got rid of some of my libraries. But you can see some of these kits. This is actually the ESP32 SMD version of the chip, and you can actually create these from scratch, and that's what I did for. No, that's not what I want. Do what I think, not what I do. All right. Let's see if I can find this. What we're going to do is I did at some point create the footprint for this Heltec board, and let's see, KiCad libraries, motor driver. That's 8266s. So PCB designs. Let's see. Do we have? I think we might have. I think we might have the PCB for this. Yeah, this is what we're going to use. So this is what it actually looks like. And so we'll be able to import this. So I'm going to add, we're going to manage our libraries. And we're going to add an existing library. And we're going to do it globally. All right, so that it is there. And I'm going to pop this. Oh, man, it's going to make me do it this way. Son of a gun. All right. Goodness gracious. I hate it when they don't let me copy paste something. PCB. And I think there should be one here. So let's see if it'll load. This will hopefully have the footprint library. If not, it's going to be, let's see where this is going to be. Oh, I think I know where it is. I put it somewhere else. Let's see what happens, folks. And we can also add libraries, footprint libraries, locally or globally. Now we're going to need to add them in the footprint library here if they don't show up. And for whatever reason, when it's browsing through these millions of combinations, it's taking a long time. So let's see if it'll load. Is it erroring out? No, it's not. Sometimes it gets stuck on something. All right. Let's see. Do we have anything? Let's see. What is this? No, that's not it. You see the frustrations that we end up with already. All right. Let's manage footprint libraries. Add globally, and this might be in this one. I did a bad job of managing where the hell these stupid libraries are. I think it might be in, actually it might be in this one here, and I believe it's in this folder. Let's try this. We're just going to keep adding folders until we get something that works. So I would have had this done earlier, but I just kind of decided 5 minutes before class what we were actually going to do. So this is as live as it gets. So once we have our footprints, and good Lord, this takes a long time. Typically, by the way, once you've reloaded your footprints, this goes instantaneously, so it all gets cached to RAM. And then you don't have to worry about how long this is taking. But it's reading through its entire freaking catalog. And then hopefully we'll have our LoRa boards in here. Come on. Always hate that last bit of the progress bar. I don't know who thought a progress bar should work like that, but let's see. All right, let's see what we get. No, there's nothing there. Lovely. Fantastic, guys. All right, give me a moment here until I figure out where the hell this has gone. Let's see if I can import this library. See if I can open, yeah, continue. No, it doesn't know what that is. Fantastic. Footprints maybe. Oh, this might be it. This might be it. All right. I think we finally found it. Preferences, manage footprint libraries. I'm going to do this globally just in case. Yeah, how about that? I have a folder called footprints. That might be where it is. Okay, let's see if we can add this in. So anything that's got like KiCad _ mod is typically the location of the libraries that we need. So we're going to let this run one more time, and then we should be able to look at the footprints for those items, and then import them into the component that we're going to use. So we're going to double check our footprints, and then we're going to go through the schematic process, and we're going to use a pull down technique for specifying the switches that we're going to use. So we're just going to pull up a simple switch circuit diagram, and I'm just going to show you a couple that we can use. All right. I don't need, is it under RF module? No, that's not it. Okay, let's see. There it is. All right, this is what we're looking for. That is our board. Okay, so we have 36 pins, more than 20 some actually, and this is the unit that we're interested in using. And I don't know if it's going to let me see the 3D view of it. Yeah, it does. This is how it would look if this were just that footprint, and this is sufficient. I actually, did I build this one from scratch? I don't remember, but here's our 36 pins that we're going to use, and that is kind of all we need. All right, and the other thing that we have is, if I could type, is a logic level converter. This, we're not going to use this. This is actually a logic level converter I think that I might have designed, and it's one that you can buy cheaply on Amazon that will do multiple in, multiple out. This lets you convert between, you know, different TTL voltages. These are really useful if your board is, let's say, 3.3 and everything else you have is 5. So here's another good footprint. All right, now that we have these, let's go ahead and get started. This is our EE schema, and what we're going to do is we're going to use the component add or the place symbol, and actually we're going to start with placing a ground, and this will take a moment. Yes, I know you can't find that. Go away. All right, so we're going to look for ground, GND, and we're just going to place this anywhere on the map. There it is. We have a ground. Let me see if I can, yeah, does it help if I zoom in? Probably. Now, a lot of people think, okay, I'm just going to place a bunch of stuff and run a bunch of wires. And that makes for a very messy schematic for those of you who haven't done this. What we're going to do is we're mostly going to use these guys over here. These are labels. And labels create your netlist just fine without needing to spend a lot of time on other things. Okay, so now let's see if we can place a component. Now I'm not placing VCC because we're providing power over micro USB to the device. So this is the device we're going to use. This is the LoRa 32, and we're going to place it right there. Cool. We're going to give this a name. This is U1. And these are the pins that should match this layout here. So if I bring this up and, oops, and, well, it's going to make me do it this way, aren't you? Okay. I guess I could have used some Windows hotkeys, but in any case, there's pins 21, 13, 12, 32, 33, and so on. So this is our device that we're going to use. So far, so good. By the way, stop me if you have any questions, or make comments, whatever you want, because otherwise I'm just assuming I'm talking to. I don't even know if I'm still live anymore. So
You're live.
okay, good. So the next thing we're going to do is we're going to just check out a pull down switch circuit. And these are very simple circuits that you can use. Let's look at this one. Open image in new tab. And we're going to use, oh, go away, block, go away, continue. We're going to use either a pull up or pull down resistor to tell the microcontroller, hey, we've got a signal. Now, what is the circuit? Well, if I have 5 volts plus a resistor, you don't ever want to do this without a resistor. By the way, you will burn something out, especially if you close that switch, you will short 5 volts and ground. So if this switch is open, this line is pulled up to close to 5 volts. When you shut the switch, it brings it down. Okay. The reverse of that is the pull down, which is when the switch is open, this circuit is pulled to ground. And when I close the switch, it's pulled up to 5 volts. So here we'd be looking for a low to high transition. Here we're looking a high to low transition. Everybody clear on that? That's all this is. Open image in new tab. That's what I was looking for. Without all the extra junk. Everybody clear on this? Make sense?
Yeah.
All right. So we're going to use a pull up resistor. And we're going to do this in our schematic here. So we're going to look at our 3v3 line because we're going to run everything in 3 volts. This is actually 3.3 volts out. This is regulated. And I'm going to put a label here, and we're going to call this 3v3. And it's going to be pointing to the right. And bam, attached. Notice that I'm not using wires where I don't absolutely have to. Yes, I could use the wire tool here, and we could do this. That would probably be fine. Okay, yes, there is a wire to ground, but I'm not a huge fan of that. And so what I'm going to do is I'm going to use tags. Now, when you're designing these, the placement of where you're putting signals and how you're routing them makes a huge difference in the difficulty that you're going to encounter in routing. So you may be tempted to just use the pins on this side, but what you're going to end up with is a potential of a lot of wires that have to cross each other or loop around or do weird things. So what I'm going to do is I'm going to make the ground plane connect at the top here. And I'm just going to have a separate ground up here. This may or may not work, and we may have to change this in the schematic and update it, but that's okay. So this is going to go to GND, and that connects this to the ground net list. So anything on that ground plane is going to be connected to that net list. Okay. Next thing we need is our switch circuit. So we're going to add a component. And we're going to look for an SPST, single pole, single throw switch. That's the, and this is a momentary switch that we're going to use, okay? And we're going to put we're going to put 4 of these. So you can just click and enter, and then I'm going to space this down, click and enter, and then click and enter. Cool. And then this, if you hit escape to change, and then we're going to give ourselves a little space here. Okay. So let's remember. Let's go back to our pull-up resistor. Come on, our pull-up resistor diagram here. And let me see if I can move this up to the side. So we're going to use pull up, right? I guess we could. Oh, it's not giving me the option. Oh, it's because KiCad does not support the Windows fancy stuff. Great. Usually, there we go. Okay, maybe it does support the Windows fancy stuff. All right, so there's our schematic. This is what we're going to do is the pull-up resistor. And the way we're going to do this is we have the switch and then we have ground. So we're going to put our labels here, and this is going to be ground. We're going to create what's called a ground plane, and I need to reverse the direction. We're going to create a ground plane so that anything that touches the ground plane will be the same thing. Now there are keys that I can press to optimize to repeatedly enter the same thing, but I'm just going to do it manually just to kind of show the entire process. Here I'm going to go ahead and use the wire tool. I could have also just put the ground wire on straight up on the second terminal of the switch. All right, so we now have the ground wire just like we do for the pull-up resistor. Now let's insert a resistor, and the resistor we're going to use is just a simple 10K. And if you just type R, that's your resistor. And by the way, once you're in the placement mode, just hitting R rotates, and that's what we're going to do. We're going to rotate. We're going to add another one here. Actually, we're going to duplicate. So duplicate has the letter C. If I just keep hitting C, it'll duplicate the last thing. It'll duplicate. Oh, come on. It'll duplicate. Maybe. All right, fine. Screw it. I'm just going to place another one. Typically, when you're in the placement mode, just hitting C will allow you to duplicate. Okay, so now we have our 4 resistors. This is going to be R1. This is going to be R2. You can make this as helpful or as useless as you want. Remember, you're the one that's going to have to deal with this. And R4. And now you can leave this as just R. What I would just do is I'd put 10K so that you know the values that you're going to use. Again, 10K. And I realize what a simple project this is, folks, but you know, it takes some effort. This is not totally effortless. So we're going to look at this step by step. All right, now I'm going to place a wire here. And the reason I'm doing the wire is because I'm going to intercept that, and that is going to be, that's going to go to my pin out here. Okay, and then I'm going to put some labels here, and they're going to go to the left, and this is 3v3. Okay, so there's one. I need to do it again. And I'm going to put here. Great, and then here. Cool. So this is now pull-up. This is a 3.3 volt pull-up. We're using 10K ohm resistors. By the way, I'm going to save this just in case we have something weird going on. And we're not done yet. We have to have the inputs to the microcontroller. So that's what we're going to do now, is we're going to put some more tags. Remember I said we're going to use pins 32, 33, 12, and 13, right? So that's what we're going to do. 32 is, and we're going to face to the right again. This is going to be BTN1. This is going to be BTN2. And of course, you have to write all this in code, right? But we're just going to assume it's there. BTN4. All right, so these are my 4 buttons. I have 1 up and down button per gate in my backyard, if that makes sense. All right, I'm not done yet because now I have to link these to these. So that's what I'm going to do. I'm going to put some labels, and we're going to have them face up. And we're going to do BTN1. And we're going to do BTN2 and 3. So these are now linked. BTN4. Now, some of you guys who have used KiCad a lot might know some shortcuts that I'm not using. That's okay. Don't worry. Let's see. If I move this, it doesn't stay connected. All right. Now we have, I believe, our entire circuit in EE schema, and I think everything else should be fine. Now we're not here. We need to put no contact or no connections here because I do not want the board router to, or the schematic editor to assume that any of these are connected. So I'm going to just put these like don't care symbols on these pins because I do not want them to be routable, period. And there we go. We're done. Now, if you want, you can run your DRC, which is your rule checker, and you just hit run, and it says, oh, I forgot to annotate these. So let me just start these. I'm going to annotate the schematics. You hit annotate, annotation complete. Now we can run the DRC to the dynamic rule checker. It says finished. I would hope to gosh that was a circuit this simple that there are no bugs. And it in fact did not find anything. If it does, it'll add little like tick marks or little pointers, arrows to show you where the error is. For instance, I can actually make this generate a problem. If I move this away, the DRC should return an error, and it should say pin not connected. And see, there it is. It says, hey, this pin is normally in use, or should be in use, but it's not. So I'm going to go ahead and reconnect that, and we'll delete the markers and run the DRC. It says, hey, everything's cool. All right, any questions about this so far? So we may run a little bit long today. I hope you'll stick with me because this is some pretty interesting stuff if you try it at home, okay? So we'll probably run right up at least until noon. I want to get to the point where we can start routing our board. I don't think we'll get to flat cam today, but that's okay. All right, next thing we're going to do is we're going to assign our footprints. That's what this button up here does, assign footprints, and it takes us to a list of devices. So this is where we click on one of these, and we're going to go to, this is our list of parts, and we're going to assign them to these footprints up here. So we're going to do resistor THT, which means through hole. And then we have a number of different options that we can pick, but we're going to do axial resistors. I think we're going to do 6.3 millimeter length, diameter 2.5, and the pitch, which is how wide apart these are going to be. I think we'll do like maybe this 5 millimeter. And I think this should be enough. Or maybe we'll do the 7. So we tell it this, and I'm going to make all the resistors the same. There it is. There it is. Now we have switches, and we want to do this single pull, single throw, and we want to use the micro switch. Now I have to remember where the hell the switches are. Button switch THT. Here it is. And we're going to use, I think Omron has little push button switches. I think these are 6 millimeter switches. These guys here, button switch. These should be the, in fact, do they have the Omron ones? Let's see. We're not using sliders or anything like that. I think we can use this 6 millimeter switch. Let me just get out my calipers and double check. Seems a bit on the small side. Well, I'll tell you what, we can always change it. If I don't have the right switch library, I will update these. But Omron usually has these. Let's try this one. I think this is the correct one, the B3F series. This is their momentary push switch. Okay, so let's try this. If it's the wrong one, we'll change it. So we have 4 of those, and then we need our Heltec LoRa 32. Where are you? I know it's here. So is it under this? Nope, it's not under there. No. Let me just find where that is. We might also be able to just do a package, but it's important that we use the footprint that we were using. If we don't, it will not work. We won't have that. Let's go to the, come on, where are my footprints for this? How is this not showing? There are several that I've imported here. I just don't know where the, And let's see if I can, well, yeah, I'm not trying to filter like that. Give me a second here, guys. Let's save apply for now. Give me a second. Let me go back to the footprint editor. This guy here. And oh, I wonder if this doesn't have, it should be there. What's it under? This is weird, guys. Not sure why my footprint editor is not coming up with this device. If that doesn't work for now, what I'm going to do is I'm going to pick a different device, and that will be sufficient for now to at least show you what's going on. Let me just go through here one more time. I'm actually not sure if there's a search function in here, which one would imagine would be there. Let's see. No. Oh, there it is. It's under footprints. Weird. Okay. So there's our Heltec LoRa 32. Oops, that doesn't belong there. That's a resistor. Resistor, through hole, axial. What did I say? 6.3 at pitch 7.2. That's what that is. Okay. So Heltec LoRa 32 is under a heading called footprints. I'm going to have to change that. And here it is, Heltec LoRa 32. Okay. Apply, save. Okay. So this is now done. And are you guys ready for the big reveal? Oh, I'm going to save my netlist as well. We're going to generate the netlist, save it there so that the PCB new can read the netlist as expected. By the way, you can create this. There's a BOM builder here, which you can generate your bill of materials. You can use some of these. For instance, this is for JLC PCB. If you want to generate a bill of materials for them to pick and place stuff for you, you can do that. We're not going to need that today. All right, now we're going to click this guy. And we will get a blank canvas. And we're going to go ahead and load the netlist. Update PCB. And there it is. There's all our crap. So I'm going to zoom in here. And this is our board up, excuse me, and our device. Now we're going to have to pick where each of these components go, whether we're going to have the microprocessor or the microcontroller in the middle, whether we're going to have it to the sides. And I think our placement is going to dictate where we're putting things. So see how we have lines kind of going mishmash across? What I want to do is I want to minimize any kind of cross wiring that I may have. So I'm going to pick apart. I'm going to rotate this because I don't want wires going across. I'm going to see what else I have going across. So sometimes the router is actually going to pick different pins based on what's proximate and what's not. So this requires patience, and doing this will mean that you will have a much easier time routing, especially on a single layer PCB. So I'm going to put some of these here, and we'll mess with this layout wise, but the important thing is we want to minimize any kind of these cross connections as much as possible. Let's see, do we have any? That does not like that. Let's see if we can see anything where you have crossing going on ends up typically being bad news. Now we're doing a one-sided PCB, so I'm going to do a couple things here. All these components, I have to flip them because right now they're on the front side of the board. So I'm going to hit the F key, and they are now flipped. When you see them pink, they are on the back side of the board. The reason they have to be on the back side of the board, ladies and gentlemen, is because when I mill this PCB, I can only mill one side. I can actually mill dual-sided, but this is a simple enough device. It will work with single side. Each one of these components then will be inserted from the back side, the unmilled portion, the blank, non-coded PCB. Let me see if I can show you. Let me see if, sure. Let's look at March 8th, 2021. Let's see if Google will show this to me. March 29th, how about that? I think that's when I finished milling this PCB. So give me a moment. Let me see if I can bring that up. All right, here we are. So this is a PCB that I milled. You'll see the parts actually have to come in from the back side because there's only one place to solder. If I put them in on the front side, I can't solder anything. Okay, so there's the PCB. This is what we're going to actually make, guys. This is what we'll see at the output of this exercise. And what it should look like is this when it's all soldered together. Okay, where I'm not going to solder every single one of these pins because most of them we're not going to use. And this is what the front side is going to look like. Very similar. Does that make sense? Does that make sense to everybody? Yes. So
Yeah.
this is what we're actually going to make, and we're going to use these little resistors. We're going to use header pins where necessary, stuff like that. Okay. These wires are where I forgot to insert a power tap for this whole damn circuit. So yes, errors happen when you're designing these at 3 in the morning because it has to be ready for a demo by 10 a.m. So yes, even faculty members end up doing a lot of cramming. So we're doing this one-sided PCB. So we had to flip everything to the back side to get this going. Let's see if we can put this. Can I put this somewhere where it's a little friendlier? Sure. This resistor still bothers me. See, as you move stuff, it gets more and more complicated. So some of these, and we may end up even rotating some of the main components out of the way to reduce the errors. So we're going to go with a pretty large footprint for now, and that's okay. I'm going to show you how we're going to route all this stuff later. And remember how I said your choice of which pin you use can have a dramatic effect in the layout options that you get. We're going to see that again. I'm going to put this resistor here, and we're going to rotate him around. So hopefully that reduces our complexity. Okay, I think we're going to get there eventually. We are going to have some crossings that we're going to have to deal with, and it is going to cause us a bit of a pain in the butt here. So we're going to simplify this as much as we can, and we'll use routing techniques to get around some of this. But I can already tell you we're going to have some headaches. Some of these are automatically going to get worked out by the following things. So the first thing I'm going to do is I'm going to go to my my edge cuts layer here. It's this icon, it's this layer here. And I'm going to make a giant polygon here that is going to define the edge of the PCB. So right now we're just going to do it like this. And our edge cuts tell us where the perimeter of the board is. Right now this is super horrible and ugly. That's okay. I'm going to redefine these later. Did I start on a boundary? I did. Okay. So we're going to go up here and double click and hit escape. And this is roughly, so if I go to the visualization, this is what this looks like so far. Notice that nothing's routed yet, and that's okay. You can see the resistors already placed on the front side. This looks horrible and ugly. Don't worry. This will all get improved soon enough. All right, the next thing we're going to do is we are going to add a filled zone to the front copper. The filled zone in this case is the ground plane that we're going to create. So I'm going to make it, I'm going to go ahead and place this, and we're going to use ground plane. I'm going to place this on the edge, the boundary of the edge cuts. There are arguments for moving it slightly inside, but I want the whole board to be covered in ground plane. Now you see these tick marks that are approaching on the side here. This means that we now have defined our ground plane. And if I hit the key B, which means fill my fill the ground plane, some of these, you'll notice that some of these paths have now disappeared because I have a board-wide ground plane that is defined. So that actually lets me simplify my design out a little bit, so that I don't have, you know, those hideous. Come on, give me a better path. So I don't have those hideous crossings going on. So yeah, we're gonna figure these out and move them until we have something that looks good, is routable. Let's see, is routable, and I think all of these should be routable at this point. Okay, so I think this is now routable. So I'm going to rotate this around, and this we'll try to make this so that it's relatively uniform. Let me rotate this. We'll put this close by. I hate it when it does these things. Almost ready to route here, folks. So, and then I'm just going to move this so it's somewhat symmetrical. Okay, all right. So now if I look at this now, it should look a lot better. Save this, and I'm going to do Alt-3. And oh, why does it look like this? Because I have to unfill the ground plane, and I have to refill it. And now when I do this, this should look roughly okay. All right, everybody with me so far with what we've done? If we look at the back side, there's our components. Again, it's not pretty. We're going to shrink it down. Don't worry. And what we go to next is this wire tool. And this follows our netlist that we're going to do. And then all we got to do is just start routing. And that's what it will do. Is that routed? Yeah. So we just start going pin by pin. You'll notice that this is the push-pull router, which, and you can use auto routers. They do work, but they often end up putting you in a bit of a pickle. And I'm not a huge fan of being put in a pickle when I'm routing. So I'm just doing a crappy job of this right now. We'll do a better job here later. But we're also what we're also going to find out is that some of this routing will not work for the CNC. It's going to give us, and we already have a problem here. I can't route around this guy. See, if I try to push pull, it's going to mess it up for me. And then if I place this one, I can't route out here. It's all broken. So we're going to mess with this. What I think I'm going to do is I'm going to route it for you guys before we meet again for our next class. And I will resolve some of these issues, and we'll pick up with a freshly routed board, and then I will show you what we need to do in order to prepare this for the CNC. If you're just sending this off to JLC PCB, this kind of routing between the pins will work perfectly fine. But if we want the CNC milling method to have the greatest chance of success, we're going to need to make these leads bigger. We're going to need, the tracks are going to need to be bigger. The clearances are going to need to be bigger, and the pads are going to need to be bigger. If we do that, I can almost guarantee that when we go to mill this on the CNC, it will work fine. And yeah, I mean, we can you know, route some of these things. But like I said, some of these are already having a problem. And, you know, we might be able to get around, you know, doing something like this, and then doing something like this, and then this. But we still have this resistor that is not routed, and that's potentially a problem because, again, I'm doing single-sided routing, and so we have a problem already. Okay, so I will have this board routed, and it always comes down to one damn track that you got to do. So I'll flip some stuff around, and hopefully we should have this all figured out. Okay, so that's all I have for you today. Oops, let's avoid the inception effect. I do want to ask if you have any questions. Any questions? I am going to show you the extra credit hint for today. Those of you who are joining us online, thank you very much. I'm going to end the recording now. We'll see you guys on Tuesday with the remainder of the PCB design and